Thank you.
All right, then let's move to Tamar. Are you ready to start your pitch?
Yeah, can you see everything okay?
Yeah, everything good. So please go ahead.
Great. So I'd like to unpack some of Antonio's ideas, specifically in the case for substitution technology. And specifically, I want to ask whether when designing these technologies, do we really need to stay very close to the body in terms of function control and integration with our nervous system, or whether we should instead consider alternative control principles, which would have interfaces that are radically different from those afforded by our own biological body, but potentially provide added functionality. And I believe the answer to this question is embedded in our brains, specifically in our sensory motor system, where we've known since the dawn of neuroscience that there exists this specific architecture to control and enable hand function. And the idea that has been capturing the imagination of the engineering community is that if we could exploit these pre-existing sensory motor pathways in order to control a prosthesis, then the user should be able, in principle, to control the device more intuitively and fluently, and maybe perhaps the prosthesis would even end up feeling like a part of the user's body. I call this vision hard embodiment, and let me just throw in a definition so that we're all on the same page. So I defined hard embodiment as a device is hard embodied if information about it is processed and used by the nervous system as information about one's own body part, and in order to accomplish the exact same function. And nothing captures hard embodiment better than Star Wars. So this is the famous scene with Luke Skywalker being fitted with his prosthesis for the very first time. And in this fitting, the interest is to make sure that the prosthesis reacts in the same way as a biological body part. Fast forward a couple of thousands of years and into our planet. Here is one of my participants. This is an avid prosthesis user. And as you can see, he's really struggling to grasp a pencil sharpener in the lab. And this is despite tens of thousands of hours of practice with this prosthesis. And the reason I show you this is to demonstrate there's such a gap between our vision for embodiment and how modern day prosthetics devices are actually interfacing with the users today. So with that in mind, I'd like to introduce to you an alternative framework today for embodiment, which calls for beyond mimicking how our brain controls the body. We should also exploit this existing biological infrastructure in order to support new solutions for improving functionality. And later in the talk, I would also try to argue that there may actually be some costs to embodiment if we follow too close to the body model. So hard embodiment I've introduced and intuitively all familiar with. In soft embodiment, I'd like to introduce the following definition. A device is softly embodied if it co-opts some of the computational bandwidth which was evolutionarily developed to sensory motor control in order to accomplish a different outcome or a different function. For me, this is an empirical framework which we can test, for example, by probing prosthesis users' experiential responses. So we can interview them and ask them how much they feel like the prosthesis is a part of their body or a part of them. So each dot here is the score of one participant, which is a prosthesis user, against their prosthesis usage in daily life. And on average, participants mildly agree that the prosthesis feels like a part of them. But importantly, those people that use their prosthesis more in daily life actually tend to agree more that the prosthesis is a part of them. So some evidence for hard embodiment. At the behavioral level, we're interested in seeing how implicitly people act and react with the prosthesis relative to how they do with a biological body part. And here we're using gesture as a framework. So we want to see if people incorporate their prosthesis while they're speaking in order to emphasize their ideas. And here we're looking at the hand prosthesis gesture ratio. So the more close to zero here, the more they incorporate their prosthesis into speech. And as you can see here, when we consider prosthesis use, those individuals who use the prosthesis more in daily life, these are the people that tell us that the prosthesis feels like a part of them, would also use the prosthesis more as a hand in a very natural and implicit way. So again, at the behavioral level, this looks like hard embodiment for us. But the key question for us is, how is the brain representing the artificial limb? And here we're going to take a little side diversion to the back of the brain, to the visual cortex, which also contains particular areas that are selective to representations of the body and body parts. And within these areas, we can use brain decoding to determine how the representation of prosthesis scales or resembles that of a biological hand as opposed to tools. And this is the result in control participants. So these are linkage trees. The shorter the branch, the more similar the representation is across two categories. And as you can see in control participants, cosmetic prostheses, these are prostheses that are designed to mimic the aesthetics of the hand, are represented very closely to hands, whereas functional prostheses, which are typically not looking like hands, are represented differently from hands and instead are clustered with tools. What about prosthesis users? So here we have a large group of participants with different levels of prosthesis use. And on average, as you can see here, both the cosmetic prosthesis and the functional prosthesis are represented quite distinctly from hands. They're also not quite represented like tools. Instead, we see that the cosmetic and the functional prosthesis are represented very similarly to each other. We can quantify this mergence of the prosthesis subcategories onto each other and away from the anchors, which are the hand and the tool, which is this prosthesis category index, which we plot here against, again, prosthesis use. And what we find here is that people that use their prosthesis more, these are the people that, talk about their prosthesis and behave with their prosthesis as if it is a part of their body. These people's brains tend to represent the prosthesis less like a hand and less like a tool and more like a prosthesis. And I think this is a really important result because it makes us realize that these existing neural loops are not doomed to function only with something that is exactly like the body or that performs the same function as the body in the same way. And I think this result invites you and others to think outside the traditional toolbox of how prosthesis should function, be controlled, or be operated. And with that in mind, thinking about alternative designs, and here are some examples from Danny Claude, my collaborator, makes us realize that if you stay too close to the body model, you're actually obscuring potential practical solutions for future artificial devices, which can actually free us from the limitations of the biological body, such as augmentation technologies. And here you see, for example, the third thumb. Finally, I want to turn to the idea that too much embodiment might actually not be necessarily so great for the user. And this is a study that I'm running together with Chris Baker at the NIH. It is still ongoing. It's very preliminary. So this is really just to kind of, make you think a bit about the question. So the question for us is, what are the unique benefits of biomimetic control strategies, if any? So if we think about a particular goal, such as opening your prosthetic hand, there's a range of potential solutions that we can use for control strategies. Some of them are biomimetic, so performing the same movement with your biological hand, and other can be completely arbitrary, such as performing the stereotypical movement in order to signal a particular gesture with a prosthesis. And we wanted to pit these two alternative control strategies head to head. Here we're using healthy participants and we're fitting them with this avatar arm, which has been developed together with CoApt. So we're using pattern recognition in order to decode EMG patterns. And then we're going to feed this into specific gestures with an eye-limb prosthesis. We train participants for 4 days, either with a biomimetic control strategy or arbitrary control strategy, over multiple gestures. And after 4 days of training, in the last day of training, or after training, sorry, we're introducing a completely novel strategy, which doesn't involve the strategies that they've learned so far. And the result I'll show you now is from the virtual egg task. So participants have.
Tamar, I think you're muted.
Sorry. So this is the virtual egg test where participants have to transport a fragile object. So in this particular task, we don't see any advantages to either biomimetic or arbitrary control. So participants perform similarly over the 4 days of training. this is, me being a bit selective. There are other tests where we see clear advantages for biomimetic control. But the interesting question for me is what happens when participants are introduced to a novel strategy. Can they generalize from what they just learned over 4 days for this new task? And what you can see here is that for the arbitrary group, performance is pretty much matched with what they've achieved over the 4 days of training. Whereas for the biomimetic group, the learning with the biomimetic strategy is not helpful when they need to adapt it to a novel strategy. So they're pretty much starting from scratch. And here for reference, we have another group that hasn't trained to use the prosthesis over 4 days, which is performing similarly to the biomimetic group. So what I'm trying to say here is that the biomimetic strategy might be intuitive, but it may not be very versatile. So if you want to think about prosthetic devices that can generalize and pick up new challenges, biomimetic strategy might not be ideal for training. I'm just going to end with the inspirational words of the performance artist Stella, who says, "What it means to be human is perhaps not to remain human at all. The body you're born with will not be the body you die with." Thank you.
Thank you, Tamar. This is wonderful presentations and lots of interesting ideas. Thanks. So just one quick question. So hard embodiment, I think this is a really interesting perspective, definition, concept to rethink about embodiment. Do you think there's a kind of boundary of any prosthetic device or other Antonio's, avatar type approach, whether there's a system that we can really accommodate as a hard embodiment or something we cannot accept as a hard embodiment? What's your views on this?
So, I mean, technically, there's lots of barriers, but if I'm just thinking more conceptually, if we could design a Luke Skywalker arm, then yeah, hard embodiment in principle should work. Why not? And we see some hints for that in brain-machine interfaces, invasive brain-machine interfaces. But again, we're thinking about the users and versatility. It's not necessarily what we want. I don't necessarily want to feel pain when I'm using my prosthesis, for example. I don't want to worry about other people touching it. So I think, so long as we're going with artificial body parts, why not break away from the biological body and think about ways we can improve on that?
We're very good at adapting to anything as long as we have to, right? And I think that's a really interesting idea. Thank you very much, Tamar.